All right, so I'm just going to give you an introduction to water ionization and acid strength. So in your workbooks, this is titled 16.1, and this begins on page 505, which I know the page numbers are a little bit screwy, but that's where we start for this one. So what we're going to do to begin with is just a review from Chem 20 on modified Arrhenius theory. So what Arrhenius said was that acids ionize in water to produce H plus in solution. And he said that bases dissociate, or they dissolve, to produce hydroxide in solution. The problem was this didn't always explain the behavior of certain substances. So we modified Arrhenius's theory a little bit to say that, well, in fact, this is a reaction with water, so we need to show that water is a reactant. If we take this example, so sodium hydrogen phosphate solid, this is an ionic compound. So the first thing that will happen in solution is it's just going to dissociate into the cation and anions. Once it's dissociated, this guy is what we call a spectator ion, the sodium, nothing will happen. But this product, the hydrogen phosphate ion, will continue to react in a second step with water. So this is actually showing water as a reactant. And because it's an acid, it's going to donate a hydrogen to water to produce hydronium in solution. Bases steal hydrogen from water, like in this example. We've removed a hydrogen to produce hydroxide in solution. So this was modified Arrhenius's definitions. Now we're going to apply this to go a little bit further in depth with our acid and bases. So this page here is just a review of all the properties of acids and bases. And if we compare a neutral solution, which is water, water is neither an acid or a base. But what sometimes will happen, like maybe 1 in a billion collisions of water molecules, that it'll actually act as both an acid and a base. So one of these will act as a base and it will steal a hydrogen from the other. So we end up with hydronium and hydroxide in solution. This is why water actually is very, very, very weak conductor. You'd need a really sensitive apparatus to actually measure that, but it does have some ions in solution. So what we call this is the ionization of water. If we set this up to solve for the equilibrium constant, so the K value for this reaction, we would have products, hydroxide and hydronium, over reactants, which is 2 water molecules. So this is what the expression would look like for our equilibrium constant. We don't include liquid water as part of the equilibrium calculation. So if we ignore liquid water, we get Kw, the ionization of water constant, is equal to concentration of hydronium times concentration of hydroxide. And the value for Kw is, it's a constant, so it's always 1.0 times 10 to the minus 14. Because we're multiplying moles per liter times mole per liter, we end up with mole squared and liter squared. If you look in your data book, on the page that has all these miscellaneous values, so page 3, it gives you the water ionization constant. So you don't need to memorize that value. It is given in your data book. So how does this all apply? Well, if you remember from Chem 20, we learned this flow chart. So it showed the connection between hydronium and pH, pH and POH, and then POH and hydroxide concentration. So if I gave you in an example problem, let's say I gave you the hydronium concentration and asked you to find hydroxide, it's going to require you to first find the pH, subtract that from 14 to get POH, and then negative log to get the hydroxide concentration, or sorry, 10 to the negative POH. Fortunately, we don't have to do that 3-step process anymore because we're going to connect this so that we have a connection all the way between hydroxide and hydronium, and how they're related is through that Kw, the ionization of water. So what it looks like now is we can go directly from here to here. So I don't have to do the 3-step process. If I know hydronium, I can use the ionization of water constant to directly find the concentration of hydroxide. So what that would look like, so since Kw equals H3O plus times OH minus, Each of those are equal to 1.00 times 10 to the minus 7. So 1.00 times 10 to the minus 7 squared gives us the Kw value. So this is the value for both H3O plus and hydroxide in a solution of neutral water. So if it's anything higher or lower than this, then it becomes an acid or base. So when water is at equilibrium, pure water, it has a pH of exactly 7, and the concentrations are both 1.0 times 10 to the minus 7 moles per liter at equilibrium. So here's a graph that shows what this reaction would look like if we were to add a stress to the system. So if I were to add some NaOH, for example, to pure water, that means I'm increasing the amount of hydroxide in solution. So if the hydroxide amount increases, the solution is going to become basic. It will adjust, the equilibrium will adjust to form a new equilibrium, but now my OH concentration is higher than H3O+. So they're no longer equivalent because there's more hydroxide than hydronium. This is going to become a basic solution. So whenever we have an imbalance of hydroxide or hydronium, then the solution is either acidic or basic. So if we flip to the next page, if I were to add hydrochloric acid to pure water at equilibrium, then H3O plus will increase immediately. It's going to establish a new equilibrium, but the concentrations are no longer balanced of hydronium and hydroxide. So as soon as I have more hydronium than hydroxide, this is going to be an acidic solution. So just based on whether or not the value is greater than, less than, or equal to 1.0 times 10 to the minus 7 moles per liter, we can determine if a solution is acidic or basic. So a couple important things to remember. For acidic solutions, the hydronium is greater than 1 times 10 to the minus 7, hydroxide is less. For basic, it's the other way around. The hydronium is less than 1 times 10 to the minus 7, and hydroxide is greater. For neutral, so for pure water at equilibrium, these are both equal. They're both balanced. So for these practice questions that I would like you to try now, so you can pause the video and try some of these practice problems. What we're going to use now, so here we're looking for hydronium, we're given hydroxide. So again, I don't have to go through this huge process, 3 steps to get me hydroxide. I can use this relationship. So Kw equals hydronium times hydroxide. So if I calculate, we'll do number 1 together here. If I look, my hydroxide concentration is 2.42 times 10 to the minus 3. So Kw equals hydronium times hydroxide. And if I'm solving for hydronium, then we're going to take Kw and divide that by the hydroxide concentration. So my hydroxide concentration is 2.42 times 10 to the minus 3. Moles per liter. And, oops, other way around, sorry. Put that on the bottom. I put my Kw value, sorry about that, on the top. So remember, that's in your data book. You don't have to memorize it. It's on page 3. It's 1 times 10 to the minus 14. Mole squared per liter squared. Divide by 2.42 times 10 to the minus 3. And that's mole per liter. So one of these will cancel. One of these liters will cancel, and we'll be left with our answer in mole per liter. So we get 4.1 times 10 to the minus 12. So since the hydroxide concentration is greater than 1 times 10 to the minus 7, and the hydronium is less, this is going to be a basic solution. So at this point, I would like you to pause the video, and I would like you to work through number 2 on page 508, all the way up to number 7, and then you can restart the video, and I'm going to go over question number 8 with you. Great, welcome back. Here's number 8 from your workbooks. And it says 6 grams of barium hydroxide is dissolved into H2O. For arrhenius/modified arrhenius, this is just an ionic compound, so it's simply going to dissociate, and if we balance it, we produce 2 hydroxide. So we know it's a basic solution. And I dissolve 6 grams of this into 450 milliliters of water. So my first step that I need to do is convert this mass and volume into moles per liter. So I've got 6 grams of barium hydroxide, and I want to cancel grams by multiplying the molar mass. So we'll have grams of barium hydroxide per mole of barium hydroxide. Molar mass is 171.35 grams. So grams of barium hydroxide cancel. So now I have moles, but I want it to be per liter. So we're going to have volume in the denominator. So 1 over liters. And the volume that we have is 0.450 liters. So this will give me my concentration in moles per liter of barium hydroxide, but I want to know concentration of hydroxide. So to cancel the moles of barium hydroxide and have moles of OH, I can use my mole ratio, which is going to be 2 over 1. And this is going to give me my concentration in moles per liter of OH. So we get an answer of 0.156 mole per liter of hydroxide, but the question wanted me to find hydronium as well. So remember, we don't have to do the 3-step thing that we did in Chem 20, we can just use Kw to go directly to that value. So Kw equals hydroxide times hydronium. I solved for the hydroxide concentration in step 1, so to find hydronium concentration, we take Kw and divide by the hydroxide. So we'll end up getting an answer of 6.4 times 10 to the minus 14 moles per liter. And again, this is basic because the hydroxide concentration is so much greater than the hydronium concentration. So for the remainder of the period, there's lots of practice questions that I'm going to get you to work on, all the way up to the end of page 512. So some of this is review from Chem 20, some of this is new where we're using the Kw value. That flowchart is in your workbooks if you want to refer back to it. And then you're going to complete these questions. So up to the end of this page here. So page 513, sorry. Page 513, number 9. So complete up to number 9 on page 513. And then we'll check them and go through them on the next day's lesson. Thanks, guys.